Hi everyone. In the last lecture we have discussed about continuous functions of self-adjoint operators, and today we are going to discuss about the spectral mapping theorem. We have already studied spectral mapping theorem for polynomials. So let us quickly recall. If T is a bounded operator and P is a polynomial, then we have shown that spectrum of P of T is nothing but P of spectrum of T. So this is nothing but set of all P lambda, where lambda is coming from the spectrum of T. So this is a spectral mapping theorem we have already studied. Now we want to ask if we replace a polynomial by a continuous function, can we obtain the same spectral mapping theorem? In fact, we can show when we can prove this result provided T is self-adjoint and f is a real valued continuous function. So theorem, let T be a self-adjoint bounded operator and f is a continuous function defined on spectrum of T and taking values in R. Then we can show that spectrum of f of T is nothing but f of spectrum of T. This is nothing but set of all f lambda, where lambda is coming from the spectrum of T. Okay. So f is a real valued continuous function defined on the spectrum of T. So to prove this result we need a lemma. First let us prove that lemma. So let T be a self-adjoint operator and f is a continuous function defined on this closed interval and taking values in R. If f is positive on spectrum of T, then we can show that f of T is positive. This result we have proved in the earlier class also, but there is a slight difference between this result and earlier result. Earlier we have shown that if the function f is positive on the closed interval AB, where a less than empty and b bigger than or equal to capital MT, and if f is positive, then f of T is positive. So here what we are doing is we are assuming that f is positive on the spectrum of T only. Then we want to conclude that still f of T is positive. So this is a slight improvement of the earlier result that we proved. Okay, so let us look at the proof. So we claim that f of T plus epsilon times identity is bigger than 0 for every epsilon positive. So from this we can conclude that f of T is positive. So let us start with some epsilon positive. Let epsilon be bigger than 0. Okay. So define a new function g of T or g of lambda as f lambda plus epsilon into 1 for all lambda in the spectrum of T. Now we know that since f is positive, g is also positive. So in fact we can show this is nothing but g is bigger than or equal to epsilon times 1 on spectrum of T. Okay. Now g is a continuous function, so we can approximate by sequence of polynomials. So let Pn be a sequence of polynomials such that Pn approximates G in the subnorm. Okay, that means we can assume that there exists some natural number n0 such that norm Pn minus G less than epsilon. So without loss of generality we can assume that norm of Pn minus G is less than epsilon by 2, less than or equal to, for every n. Otherwise we can actually, there is some n0 depending on epsilon such that norm Pn minus G less than epsilon by 2 for all n bigger than or equal to n0. So we can relabel those polynomials as P1, P2, P3 again to get this condition. So that means we can say that G minus epsilon by 2 into 1 is less than Pn, that is less than or equal to G plus epsilon by 2 into 1. This is true for every n. So that means, so Pn is bigger than or equal to G minus epsilon by 2 into 1, but G is nothing but f plus epsilon. So this is f plus epsilon by 2 into 1. That means Pn's are bigger than or equal to epsilon by 2 into 1 on spectrum of T, because we are approximating G on spectrum of T only. From this we can conclude that Pnt is bigger than epsilon times identity, but we know that Pn converges to G, so G of T is bigger than or equal to epsilon times identity, and we know that G of T is f of T plus epsilon, so this implies f of T plus epsilon by 2 times identity is bigger than, and since epsilon is arbitrary, so we can say that f of T is positive. Okay, so this proves the lemma. Next we want to prove the spectral mapping theorem. Okay, so let us look at the proof. So we want to show that spectrum of f of T equal to f of spectrum of T. So first we want to show that f of spectrum of T is contained in spectrum of f of T. So let us take lambda naught in the spectrum of T. We want to show that f of lambda naught is in the spectrum of f of T. That means we want to show that f of T minus f of lambda naught identity is not invertible. Choose a sequence of polynomials such that Pn converges to f uniformly on spectrum of T. Okay, so then we have if you look at Pn of lambda naught, this converges to f of lambda naught, and Pnt converges to f of t. So hence we can say that f of t minus f of lambda naught into identity, this is nothing but limit n tends to infinity Pnt minus f of lambda naught, sorry, this is Pn lambda naught into identity. Okay, now we know that Pn of lambda naught is inside in Pn of spectrum of t, because lambda naught is coming from the spectrum of t. This is by spectrum mapping theorem, it is spectrum of Pn of t. That means we can say that Pnt minus Pn lambda naught is not invertible for all n in n. So from this we can say that now Pnt minus Pn lambda naught converges to Ft minus f of lambda naught times identity. Now since this Pnt minus Pn lambda naught identity is not invertible and set of all non-invertible elements is a closed set, so we can conclude that f of t minus f of lambda naught I is not invertible in B of h. So therefore we can say that f of lambda naught is inside spectrum of f of t. Okay, so we have taken lambda naught from spectrum of t and shown that f of spectrum of t is contained in spectrum of f of t. So we want to show the other way inclusion. So we want to show spectrum of f of t is contained in f of spectrum of t. So let us take mu which is outside f of spectrum of t. Let mu is f of, we want to show that mu is not in the spectrum of f of t. Now define g of t as f of t minus mu into the constant function 1. This is for every t in spectrum of t. Now clearly g is non-negative, g of t is non-zero for all t in spectrum of t. If g of t naught equal to 0 for some t naught, then f of t naught will be mu, and that means mu is in f of spectrum of t, which is a contradiction. Okay, now g is continuous on the compact set on spectrum of t, and since it is continuous on a compact set, it attains maximum and minimum. Hence, and since this is non-zero, there exists some epsilon positive such that mod g of t is bigger than or equal to epsilon for all t in spectrum of t. So this implies that g of t square is bigger than epsilon square for every t in the spectrum of t. that means G square is positive on the spectrum of T. Now from this we can conclude that from this G of T square is bigger than epsilon square identity by the continuous functional calculus, and this implies G of T square is invertible, so hence this is invertible. Now G of T square is a positive operator because G of T is self-adjoint. This we have already observed in the earlier lecture, and G of T square is a positive operator which is bigger than epsilon identity. So we use the following result. Recall, let T be a bounded operator which is positive. Then T inverse exists and bounded if and only if there exists some epsilon positive such that T is bigger than epsilon times identity. Okay. Now using this result we can conclude that G of T is invertible. Once G of T is invertible, that means F of T minus mu is invertible. So hence we can say that mu is not in the spectrum of F of T. So GT not invertible, GT is invertible implies F of T minus mu I is invertible. That means mu is not in the spectrum of F of T. So what we have shown is we have taken mu outside F of spectrum of T, and we have shown that it is not in the spectrum of F of T. So from this we can conclude the result. So this is the proof of the spectral mapping theorem. Okay. Now earlier we have discussed that if you take the map from CAB to B of H, it is denoted by eta. So F going to F of T, where T is self-adjoint. We have only shown that norm F of T is less than or equal to sup norm of F. So this preserves all the operations of CAB, namely linear space structure, multiplicativity property and the adjoint, but it is not an isometry. But if you look at F of T is a self-adjoint operator, hence we can say that norm of F of T is exactly spectral radius of F of T. This is nothing but supreme of mod F lambda, where lambda is coming from spectrum of T. This is by the spectral mapping theorem. So let us call this as, this is called spectral norm. So with respect to this norm we can say that eta is an isometry. That means if you define eta from CAB into now the question is, can we say this is an isometry? Still we cannot say that this is an isometry, because the spectral norm is defined on the spectrum of T only, but our function is defined on closed interval AB, where A less than or equal to MT and B is bigger than capital MT. Let us take F from the spectrum of continuous function defined on the spectrum of T, and of course it is a real valued function. Then we can actually extend this to the close interval empty comma capital MT, then by the T's extension theorem, there exists f hat which is continuous on this such that now f can be written as restriction of f hat to the spectrum of T. So we know that spectrum of T is subset of this interval, close interval MT comma capital MT, and we know the continuous functional calculus for capital FT. So hence we have f of t, we can write f hat of t because f hat is an extension of f. Hence we can from this we can conclude that norm of f of t is nothing but norm of f of t, and this is nothing but spectral norm of f. If we know how to define f hat of t by the because we have already studied this continuous functional calculus for functions defined on this kind of intervals. In fact, we have taken a strictly less than mt and b bigger than or equal to capital MT, but the same thing is true for this interval also. Now the conclusion is the following, that if you define a map alpha from CAB with spectral norm into B of H, here we can take C of spectrum of T which sends f into f of t, because f of t is defined restriction of f hat of t to the spectrum of t. Now this functional calculus actually is an isometry. It preserves all the properties. It preserves the adjoint, it preserves the multiplication in C of spectrum of t. So we can easily check that this alpha is linear, it's an isometry, alpha fg is alpha f into alpha g. And in fact we can show that alpha since f is real, so we can actually say that whenever f is positive implies f of t is positive, that is alpha f, this is positive. Okay, so this is called the continuous functional calculus for self adjoint operators. Okay, so I'll stop here. Thank you very much.